Chairman is authorized to declare recess at any time. Before I deliver my opening remarks, I wanted to note that today the committee is meeting virtually. I want to announce a couple of reminders to the members about the conduct of this hearing. First, members should keep their video feed on as long as they are present in the hearing. Members are responsible for their own microphones. Please also keep your microphones muted unless you are speaking. Finally, if members have documents they wish to submit for the record, please email them to the committee clerk, whose email address was circulated prior to the hearing. I now recognize myself for an opening statement. Good morning, and thank you to all of our witnesses who are joining us virtually here today to discuss the importance of climate and energy science research at the Department of Energy. This hearing is one of a series on research and development activities sponsored by the DOE's Office of Science. This office was funded at over $7 billion in fiscal year 21 and accounts for over half of DOE's non-defense R&D budget. The energy sciences and climate research programs were each funded at over $2 billion and $750 million in fiscal year 21, respectively. Today, we will just be focusing on these two programs, though there are others that we will examine in the months ahead. While these investments are not insignificant by any means, they are simply not enough to tackle the climate crisis. This research is not just a nice to have, it is a must have for the safety, security, and future of humanity. The Basic Energy Sciences Program is one of our nation's biggest sponsors of research in the natural sciences. This research helps us understand matter and energy down to the atomic level to ultimately inform advances in a broad range of green energy technologies. The great example of this work is battery technology development, which we will hear much more about today. Understanding the materials, properties of various building blocks of batteries, and being able to observe how batteries perform in real time at the molecular level, this is the kind of cutting-edge scientific research we need as we drastically reduce greenhouse gas emissions. We should also keep in mind, however, that solving the climate crisis is not only a technological challenge. To meet our climate goals, as the Intergovernmental Panel on Climate Change has said, will take rapid, far-reaching, and unprecedented changes in all aspects of society. And as the Biden administration has made clear, these changes can and must lift up workers, the poor, and redline communities of color who are already hardest hit by the fossil fuel economy and the impacts of a warming planet. Bold climate action can create millions of jobs, union jobs, and make life better for all. And we already have the technologies we need to go all in on the transition. Here too, research at the Department of Energy has a crucial role to play. I am pleased that we are joined today by experts who can speak to the interdisciplinary research and new kinds of collaborations we need. That includes more integration with the social sciences to help us deploy existing green technologies faster and better in ways that promote justice and build community power. Let's learn by doing and plug those lessons into science research and technology development as we go. We also have distinguished witnesses present today who will discuss the climate science activities carried out by DOE's Biological and Environmental Research Program. This research helps us understand complex Earth systems, the accelerating impacts of climate change, and how we can better protect people and infrastructure. It also aims to improve our understanding of regional differences in climate and Earth systems at a more granular level to help inform policymakers. This kind of data would be incredibly useful from my district, as I've seen firsthand how communities are dealing with climate impacts like flooding and extreme heat, which are compounded by failing infrastructure and other forms of environmental justice. One of the most important features of these programs are the operation and maintenance of state-of-the-art scientific user facilities. These facilities attract some of the world's most talented researchers from academia and industry. They range from giant synchrotron light sources to nanoscale research facilities, all of which are used to imagine and understand the fundamental properties of materials and chemical processes for a wide range of clean energy, medical, and other important applications. The Office of Science also supports field observatories around the world that measure atmospheric data that feed into climate models. But the research infrastructure is only one piece of the puzzle. We need people, talented and trained professionals, to perform this research and help lead us into a green, just future. And we need to increase the participation of marginalized communities, including with STEM education infrastructure and workforce pipelines that will unleash the talents of students of color who have been neglected. This is a topic that is near and dear to my heart, and I am proud that this committee is working to make our research activities more inclusive at every level through various legislative proposals. I want to again thank our excellent panel of witnesses assembled today, and I look forward to hearing your testimony. That now recognizes Weber for an opening statement.
All right, thank you, Mr. Chairman. I appreciate that, and thank you for hosting this hearing. And we want to say thank you to our witnesses and our witness panel for taking the time to be with us today. Passage of the Energy Act of 2020, comprehensive bipartisan energy legislation, which became law at the end of the last Congress, was a giant leap in the right direction when it comes to updating U.S. energy policy and deploying a diverse portfolio of clean next generation power sources. But the applied energy activities authorized by the Energy Act only represent, quite frankly, about half of the Science Committee's jurisdiction at DOE. The other half is the Department of Energy's Office of Science, a $7 billion with a B dollar program that oversees 10 of DOE's national labs and 28 user facilities. Armed with the most cutting-edge tools of modern science, like advanced light sources, particle accelerators, and 2 of the top 5 fastest supercomputers in the world, the Office of Science has made invaluable contributions to the United States scientific progress. This office has repeatedly demonstrated that basic science research is the most effective way to encourage the development of those kinds of new technologies we're seeking. But as I speak here today, other countries like China are making significant investments in science and threatening our global leadership when it comes to innovation. That is why the department's continued investment in basic and early stage research is vital to maintaining our technological edge. And I'm proud to report that we're in the middle of a bipartisan process to reauthorize the Office of Science, which will invest in the facility upgrades and basic infrastructure that attracts and retains the absolute best scientists in the world. As part of that reauthorization process today, we'll focus on 2 specific programs within the Office of Science: Basic Energy Sciences, BES, Biological Environmental Research, BER. At the simplest level, BES researchers discover new materials and designs new chemical processes. While this touches virtually every aspect of our energy resources, the ultimate goal of the program is to better understand the physical world and harness nature to benefit people and society as a whole. Pretty powerful stuff. BES's focus includes material science research that leverages DOE advanced computing resources to aid in the development of novel materials used to make energy production, energy storage, and use cleaner and more efficient. Just last Friday, I introduced HR 2950, the Computing Advancements of Material Science, or CAMS Act, which in part establishes DOE computational materials and chemistry science centers and a materials research database. I'm excited to hear from our panel of witnesses, including Dr. Kristen Pearson from Lawrence Berkeley National Lab, on how applying advanced computing capabilities to material science will accelerate our progress in developing those very exact new clean energy technologies. The BER program, the other subject of our hearing today, is more focused on the natural world and aims to uncover nature's mysteries involving genomics, plants, ecosystems, and complex earth systems, in an effort to re-engineer microbes and plants for energy as well as other applications. In this capacity, BER also plays a unique and essential role in researching the relationship between the atmosphere, ocean, land, and us humans to improve climate and Earth system models. I look forward to hearing from all of our witnesses on how they've utilized the many user facilities, the tools, and the collaborative resources that both BER and BES have to offer, and what groundbreaking discoveries are right around the corner as a result. We'll see if Ms. Kristen can pontificate on the future. I'd like to take a moment to thank my friends across the aisle, Mr. Chairman, for holding this hearing and making it bipartisanship a priority when it comes to this kind of legislation. It's a good thing. We appreciate that. Been a long time coming, but I'm beyond excited to think we are shaping the future of science and energy through the focus on the Office of Science. Thank you again for all the witnesses for being here. I look forward to their testimonies. And with that, Mr. Chairman, I yield you back 2 seconds.
Thank you. The chair now recognizes the chairwoman of the full committee, Ms. Johnson, for an opening statement.
Thank you very much, Mr. Bowman. Good morning to all. I'm appreciative of you holding this important hearing today and want to thank all of our esteemed witnesses that are here. Today, we meet to discuss the pioneering research supported by the Department of Energy's Office of Science and how the national laboratories, major facilities, and cutting-edge programs that it stewards are leading our nation to a cleaner energy future. The office's Basic Energy Science Program, or BES as we call it, is the nation's largest sponsors of research in the physical sciences, supporting research at nearly 170 universities, laboratories, and other research institutions throughout the U.S. The program also currently oversees 12 national user facilities, 2 energy innovation hubs, and 41 energy frontier research centers tasked with finding solutions for our nation's greatest energy challenges. Many significant innovations can be traced to decades of BES research, and such as the LED lighting, efficient solar cells, better batteries, improved production of processes for high-value chemicals, and stronger, lighter materials for transportation, nuclear power, and national defense applications. The program is also instrumental in fostering the next generation of scientists, which echoes the importance of our nation's continuous support of STEM education from K-12 through the doctorate degree level. Not to be overshadowed, the Biological and Environmental Research Program, or BER, seeks to equip our leading researchers and policymakers with the knowledge and tools necessary to better understand and predict the behavior of biological, climate, and other environmental systems. BER supports atmospheric ecosystem research at all levels, from microscopic to field scale. This work is carried out by scientists at universities and other research institutions across the nation, and is further enabled by the 2 state-of-the-art user facilities, the Atmospheric Radiation Measurement Facility and the Environmental Molecular Science Laboratory. The research supported by BER is ultimately provide us with a more holistic and predictive understanding of our climate and environment that accounts for regional and temporal variations and considers the complex impacts they have on human behavior. That in turn will enable us to better anticipate shifts in our climate and to design and develop more efficient and resilient energy generation systems and infrastructure. Today's witnesses should know that it is a priority for this committee to strengthen and support the scientific capabilities of our national labs and universities. So I look forward to our distinguished panelists sharing their perspectives, not only on future research, pathways to solve grand challenges, but also how we can expand access to the unique capabilities of these critical facilities and programs. Thank you, Mr. Chairman, and I yield back.
Thank you, Madam Chairwoman. The chair now recognizes the ranking member of the full committee, Mr. Lucas, for an opening statement.
Thank you, Chairman Bowman, for hosting this hearing. And thank you to all of our witnesses for being with us today. The Department of Energy is the largest federal sponsor of basic research in the physical sciences and is a world leader in science and technology innovation. Through its Office of Science and National Laboratory System, the department supports research across scientific disciplines and plays a lead role in U.S. research and development ecosystem. Today, we have an opportunity to examine the activities of two of the Office of Science programs, the Basic Energy Sciences and the Biological and Environmental Research. These two programs cover a wide variety of high-priority R&D initiatives, from advanced material science and biochemistry to geoscience and climate systems modeling. The science impact of BES and BER cannot be overstated. BES funds basic research at more than 150 U.S. academic, private sector, and nonprofit institutions, and its user facilities support approximately 16,000 scientists and engineers each year. Over the past 40 years, BES research has led to major discoveries in solar cells, battery technology, advanced transportation materials, manufacturing processes, nuclear power, and LED lighting. The other program we're considering today, BER, has helped redefine modern biotechnology through the Human Genome Project, and since the 1950s has driven innovation in U.S. cutting-edge U.S. environmental science, system sciences. Today, BER is accelerating the capacities of complex Earth system models using large-scale data and high-performance computing. This is the kind of fundamental research that will not only enable the development of next-generation technologies, but will also support U.S. competitiveness in science and establish our global leadership in the industries of the future. This is why my bill, the Securing American Leadership in Science and Technology, SALSTA, which creates a long-term strategy for investment in U.S. research and infrastructure, includes a comprehensive reauthorization of the DOE Office of Science, roughly doubling the funding for programs like BES and BER over 10 years. SALSTA also provides specific funding for key DOE national laboratory user facilities, like the light sources and neutron sources that enable BES work. And it establishes a program for the development and construction of BER user facilities. I'm also proud to join my colleagues on two bills to strengthen the work done by BER and BES. Last week, Randy Weber, the ranking member of this subcommittee, introduced the Computing Advances for Material Science Act, which will create a program at DOE to apply advanced computing practices to material science research challenges. And my colleague, Representative Barrett of Indiana, introduced a bill today to reauthorize bioenergy research centers and create user facilities to help us address complex challenges in environmental science. These bills are important steps forward in improving our nation's clean energy research. This hearing comes at a critical time in our conversation on the state of our federal R&D enterprise. Lately, we've heard a lot of talk about big investments in American innovation, but at this moment, we face very real threats to our global scientific leadership. Only serious proposals can be considered. Maintaining U.S. leadership in science and technology will require a shared commitment to prioritize DOE and its Office of Science. And let me be clear, any American R&D investment plan that lacks this commitment is fundamentally flawed. The Science Committee may not agree on everything, but we've always been united in our support of the Office of Science. This Congress, I look forward to continuing to work with Chairwoman Johnson and my friends across the aisle on bipartisan Office of Science legislation that will make a strong commitment to the success of programs like BER and BES and ensure the long-term stability of our international leadership in science. I once again want to thank our witnesses for being here today, and I look forward to a productive discussion. Thank you, Chairman Bowman, and I yield back the balance of my time.
Thank you, Mr. Lucas. If there are members who wish to submit additional opening statements, your statements will be added to the record at this point. At this time, I would like to introduce our witnesses. Dr. Kristen Pearson is a professor in materials science and engineering at UC Berkeley with a joint appointment as faculty senior scientist at the Department of Energy's Lawrence Berkeley National Laboratory, where she also serves as director of the Molecular Foundry. She has published more than 200 papers in peer-reviewed journals, holds several patents in energy applications, and is among the world's 1% most cited researchers. Dr. Fikile Brushett is an associate professor of chemical engineering and Cecil and Ida Green Career Development Chair at the Massachusetts Institute of Technology. His research group focuses on advancing the science and engineering of electrochemical technologies needed for a sustainable energy economy. Dr. Brushett received his bachelor's in chemical engineering from the University of Pennsylvania, a master's and PhD from the University of Illinois Urbana-Champaign, and was a postdoc at DOE's Argonne National Laboratory. Dr. Esther Takeuchi is a SUNY Distinguished Professor and the William and Jane Knapp Chair in Energy and the Environment at Stony Brook University. She holds a joint appointment at DOE's Brookhaven National Laboratory as Chief Scientist and Chair of the Interdisciplinary Science Department. She is also a director of an Energy Frontier Research Center funded by the department. Dr. Keuchi is a member of National Academy of Engineering, was awarded the National Medal of Technology and Innovation by President Obama, and was inducted into the National Inventors Hall of Fame. Dr. Shubin Zheng is the Agnes N. Hori Chair in Environment, Professor of Atmospheric Sciences, and Director of the Climate Dynamics and Hydrometeorology Center at the University of Arizona. Through over 200 peer-reviewed papers, Dr. Zheng's research has focused on land, atmosphere, ocean interface processes, weather and climate modeling, hydrometeorology, remote sensing, and big data analytics. He also serves on the Science Advisory Board of the DOE Pacific Northwest National Laboratories Earth and Biological Sciences Directorate and the Science Advisory Board Environmental Information Services Working Group of the National Oceanic and Atmospheric Administration. Last but certainly not least, Dr. Narcima Rao is an associate professor of energy systems at the Yale School of the Environment. Dr. Rao has 2 decades of global experience in energy, first as an energy consultant and for the last decade as an academic. Dr. Rao's research examines energy systems, climate change, and human development. He is particularly interested in equity in energy transitions and the impacts of climate change and its mitigation on poverty around the world. Thank you all for joining us today. As our witnesses should know, you will have 5 minutes for your spoken testimony. Your written testimony will be included in the record for the hearing. When you all have completed your spoken testimony, we will begin with questions. Each member will have 5 minutes to question the panel. We will start with Dr. Pearson. Dr. Pearson, please begin.
Thank you. Chairwoman Johnson, Ranking Member Lucas, Chairman Bowman, Ranking Member Weber, and distinguished members of the committee, thank you for inviting me to testify today. My testimony is my own and does not necessarily reflect the views of the U.S. Department of Energy or the University of California. I'm an immigrant and a naturalized citizen, and basic energy science has touched virtually every aspect of my scientific career in the U.S. My testimony is based on my leadership roles in 3 BES programs: the Joint Center for Energy Storage Research, JCESR, the Materials Project, and the Molecular Foundry. I also have a strong connection to industry and the applied sciences, which allows me to observe how basic energy science insights translate into technological solutions. As you know, BES provides world-leading expertise and instrumentation to advance fundamental knowledge. It also provides training of our next generation scientists. And from my experience, BES funding provides a foundational platform for future-looking innovation leadership, democratizing the access to knowledge and workforce development. For example, on innovation leadership, the materials used today in lithium-ion batteries were first studied in the 70s and 80s at places like Bell Labs, national laboratories, and universities. Today, the main question that I get from investors and EERE is, how do we deal with the mineral resource limitations? Our current lithium-ion batteries can't operate well without some of these metals, for example, cobalt. However, our most promising next-gen materials are quite different than our current ones. And these materials are directly related to strong long-term investment in the understanding of how ions arrange and how they move in battery materials. To support future innovation, the Energy Storage Hub at Argonne, J. Caesar, focuses on beyond lithium-ion chemistries. And as one major breakthrough I can mention, J. Caesar has uncovered the fundamental reason why we don't have high energy density magnesium and calcium batteries like lithium. J. Caesar has now turned that knowledge into a discovery vehicle for the development of new materials with increased stability, and we currently hold the world record in new liquid formulations. The Materials Project is a BES-funded Materials Genome Initiative Software Center, and today it's the world-leading materials data platform. It provides a stellar example of the impact of basic energy science in democratizing knowledge and accelerated learning. The Materials Project uses high-performance computing to calculate the foundational properties of materials rather than measuring them, which is so much faster and cheaper. For example, measuring even one property by traditional means across tens of thousands of materials, that would take decades and millions of dollars. And we can calculate it in a matter of weeks to months. This high value and pre-competitive materials data is then made available free of charge to the world. Every day, tens of thousands of users, diverse minds and innovators access this data to train machine learning algorithms to develop novel materials that support our future energy solutions. Our audience has been growing exponentially since we started. The Materials Project is now approaching 200,000 registered users. And finally, the nanoscale science research centers, the NSRCs, are BES-funded user facilities, one of them being the Molecular Foundry. They are knowledge-based centers for interdisciplinary research at the nanoscale, where access to leading expertise is as important as access to state-of-the-art instrumentation and resources. Electron microscopy is one of those resources. And now, hopefully, thanks to the wonderful virtual format of this hearing, I'd like to take you to California. This is the Molecular Foundry. This is the user facility where we house, for example, the TEAM microscopes. The TEAM microscopes are a product of multi-institution industrial collaborations funded by the BES. They were the best in the world in 2009, and they're still a critical resource today. The picture you're seeing here is an iron platinum nanoparticle where we can image exactly where each atom sits and correlate that to the knowledge of its magnetism. And this is fundamentally important for new applications in next generation hard drives. This is just one of the hundreds of free of charge capabilities that the Foundry provides. And each year, the Foundry supports roughly 1,000 users, including academics, students in training, small businesses, and 2/3 of these are early career scientists. It's a shining example of how BES-funded science democratizes both the expert knowledge as well as high-value instrumentation, which enables a broad spectrum of today's breakthroughs and contributing to the next generation workforce development. These are some of the many vital roles that BES science plays in the US innovation ecosystem. And without sustained investment, we shortchange and stall technological advances so necessary for our future generations. Thank you for listening, and I look forward to taking any questions.
Thank you, Dr. Pearson. Dr. Brushett, you are now recognized.
Thank you. Chairman Bowman, Chairwoman Johnson, Ranking Member Weber, Ranking Member Lucas, and distinguished members of the subcommittee. I'm honored to testify before you here today at this hearing. My name is Fakile Brushett, and I'm an associate professor of chemical engineering at the Massachusetts Institute of Technology. I'm also a contributor to the Joint Center for Energy Storage Research, J. Caesar, an energy innovation hub sponsored by the Department of Energy's Basic Energy Sciences program. My research program at MIT focuses on advancing the science and engineering of electrochemical technologies needed for a sustainable energy economy. My principal research interest has been the development of redox flow batteries, which have the potential to enable such a transition by facilitating the integration of intermittent resources like wind and solar into the electric grid, as well as by optimizing existing grid infrastructure. While state-of-the-art redox flow batteries have achieved niche successes, present embodiments are too expensive for ubiquitous adoption. We are vigorously pursuing opportunities for transformative advancements that will change these economics. My group, along with others, are searching for inexpensive electrolyte formulations, developing high-performance electrochemical reactors, and working to establish manufacturing capabilities for battery systems and the materials and components they're made of. We work on these important problems with other academics, with national laboratories, and with industry. JCESR has truly served as a hub for these collaborations, without which I would have sought other, safer directions, and my group's progress in flow batteries would have been slower and ultimately our work less impactful. So let me tell you how BES has supported the career development path I've taken. When I finished my graduate thesis at the University of Illinois at Urbana-Champaign, I knew I wanted to apply my training to problems in energy storage. An appointment as a director's postdoctoral fellow at Argonne National Laboratory provided a rapid entrance into my newly chosen field. There, dozens of research professionals with diverse scientific backgrounds were working in the battery group, addressing an interconnected set of problems from modeling the chemistry inside an electrochemical cell at the atomistic level to building and breaking large battery packs. I was immersed in battery science and engineering and learned much from this vibrant research community surrounding me. I also had easy access to experts at Argonne's cutting-edge facilities. I could grab coffee with the beamline scientists at the Advanced Photon Source, or have lunch with a synthetic chemist from the Center for Nanoscale Materials. I learned new science, expanded my research skills, and was inspired to explore new research directions. Beyond research, I was also able to develop other important skills essential for running a successful group. Things like project management, scientific leadership, and best practices in environment, health, and safety. My postdoc at Argonne also provided an opportunity to participate in writing what would become the winning proposal for an energy innovation hub focused on energy storage, JCESR. Thus, when JCESR ramped up at the same time I started at MIT, I was able to secure research funding for my group, pursue ideas that I had helped to develop, and gain immediate visibility both at MIT and within the energy research community. My own experience at Argonne, first as a postdoc and now as a JCESR researcher and team leader, opened my eyes to educational and scientific opportunities the DOE offers young scientists and engineers through the national laboratories. Opportunities I now often suggest to undergraduate students, graduate students, and postdoctoral associates I mentor at MIT. In conclusion, while I have undoubtedly benefited from the research environment at MIT in terms of student education, faculty mentoring, fundraising, and fruitful collaborations, my engagement with JCESR has added another dimension, accelerating my career growth as a scientist, as a teacher and mentor, and as a leader. Thank you for the invitation to testify before the subcommittee. I would be happy to answer any questions you or other members of the committee may have. Thank you.
Thank you, Dr. Brushett. Dr. Takeuchi, you are now recognized.
Good morning, Chairman Bowen, Ranking Member Weber, Chairwoman Johnson, Chairman Lucas, committee members. Thank you very much for the opportunity to speak with you today. I draw on my experience of several decades in industry, leading a research and development group in battery manufacturing, as well as my current position where I'm a joint appointee at Stony Brook University as a faculty member and a member of Brookhaven National Lab. Let me start with a few words about the energy landscape. It really is imperative to rapidly change the energy landscape in order to address not only resiliency, but environmental sustainability. The two opportunities that I want to describe for you today are electrification of transportation and broadening adoption of renewable energy into the electric grid. And both of those opportunities depend on energy storage. Specifically, I'm going to talk about batteries. What batteries do is take chemical energy and reversibly allow electricity to be delivered. When I was in industry, I developed a battery for the implantable cardiac defibrillator. While that battery works very well for its application, it's entirely different than the batteries in our laptop computers, the batteries in electric vehicles that are much larger, and now we're talking about even larger batteries for the grid that must last 10 or 20 years. So lifetimes and size keep both increasing. In terms of research and development structure, complex problems such as energy storage are best addressed in teams. I'm the director of an Energy Frontier Research Center funded by BES. This is a vehicle that has allowed me to pull together a team of highly talented researchers on their own and focus them collectively to address items that they could not address singly. From 2014 to 2018, we probed the question of the balance of batteries delivering electricity and heat. If we can minimize heat, they become more efficient. And now we're looking into the fundamental science of making batteries big, meaning scalable. Researchers, talented researchers need tools. When I started my career, the best way to figure out what was happening in a battery was to test it, cut it open, and look at the pieces. Today, I can go to facilities such as the National Synchrotron Light Source 2 at Brookhaven National Lab. I can probe a working battery using the high energy X-rays, strong enough to visualize what's taking place inside a sealed battery in real time. This information really accelerates ability to develop and visualize next generation batteries because we have unprecedented information. Our findings in the EFRC have also led us to be able to work with more applied programs in the Department of Energy. Some of the materials findings, we're working with the Office of Electricity to probe whether these ideas are relevant to large-scale batteries with water-based electrolyte. We're working with the Vehicle Technologies Office, part of the EERE, to investigate fast charge, meaning 10-minute charge of vehicle batteries. That technology approach we patented, and now we have follow-on funding from the Technology Commercialization Fund to demonstrate that approach at scale. Workforce development and interacting directly with next generation scientists was one of the major drivers for me to leave industry and move to academics to be able to shape and inspire the next generation of scientists and leaders. The EFRCs provide a venue where young investigators can be supported, gain insight into national lab, academic, and collaborative research, and frame their careers for the future. So in closing, I want to highlight that availability of clean, reliable energy directly correlates with standard of living and the quality of human life. We must ensure that this is the case. Transformation of our energy landscape is an imperative. That's why the investments by DOE and BES are so critical. Let me be clear, this is a race. There are significant global investments, and these investments over the next several years will determine not only the energy landscape, but whether the United States maintains an opportunity to lead. Thank you very much for your time, and I look forward to questions.
Thank you, Dr. Takeuchi. Dr. Zhang, you are now recognized.
Chairman Bowman, Ranking Member Weber, Chairwoman Johnson, Ranking Member Lucas, and the members of the subcommittee. Thank you for the opportunity to be here today to discuss climate and environmental science research at the Department of Energy, or DOE. Starting this week, I begin to co-chair the scientific steering group of the Global Energy and Water Exchange Project, which is one of the major international programs on climate and water sciences. My testimony today draws on my extensive leadership experiences and publication record of over 200 peer-reviewed papers. I will briefly cover 4 topics: current status of the DOE research, unique aspects, major challenges, and future directions. For the current status, DOE programs support 3 primary research activities on the atmospheric system, environmental system, and Earth and environmental systems modeling. This portfolio also supports 2 scientific user facilities, the Atmospheric Radiation Measurement Facility and the Environmental Molecular Sciences Laboratory. In particular, the modeling program supports the development of the DOE Energy Exascale Earth System model. To illustrate the success of these activities, here I share just one example. DOE's climate model version 1 was released in 2018, including a unique capability to zoom in for a closer look at the particular region, such as the US. More recently, a new global cloud permitting modeling capability at 2-mile grid spacing has been developed, making this model the world's highest resolution climate prediction capability. Regarding the uniqueness, 4 unique aspects of DOE's research efforts can be identified. First, DOE climate model stands out for being the first Earth system model of its kind to be run on the ultra-fast supercomputers, that is, exascale computers developed by DOE. Second, DOE emphasized extreme weather under global warming and geographic domains that exhibit sharp gradients, such as coastlines and complex terrain over Western US. Third, DOE is integrating its human system model with its climate model. This represents the world's first attempt to develop a fully coupled human Earth system model to make more consistent and realistic predictions. Finally, DOE's user facilities are world-leading in the relevant fields. For instance, the comprehensive observatory approach using ground and airborne measurements is now widely adopted by other national and international programs. At the same time, DOE's research faces several major challenges. In integrating Earth system modeling with exascale computing, in understanding the predictability of the fully coupled human Earth system, and in keeping up with new observing technologies for the user facilities. Based on these discussions, the future directions include several areas. First, global cloud permitting model with a grid spacing of 2 miles should continue to be developed for exascale computers. Also needed is the use of innovative artificial intelligence for coupled human and natural system modeling, uncertainty quantification, computational efficiency, and model process representation. Second, closer collaborations with DOE applied programs are needed to assist in the planning of our nation's energy and related infrastructure. In particular, this planning can be assisted by trade-off and scenario analysis using fully coupled human Earth system modeling. Third, DOE user facilities need to keep up with new capabilities, and enhanced data service is needed to expand the user base and help convert data into knowledge. DOE also needs to proactively reach out to minority-serving institutions and historically Black colleges and universities. Besides interagency collaborations, the coupled human Earth system modeling capabilities can also assist the private sector on topics like extreme events under climate change. Finally, DOE can benefit from and contribute to the new initiative of the World Climate Research Program on Digital Earth, which is a dynamic representation of the Earth system based on optimal blending of models and observations. Thank you.
Thank you very much, Dr. Zhang. Dr. Rao, you are now recognized.
Chairman Bowman, Chairwoman Johnson, Ranking Member Weber, Ranking Member Lucas, distinguished members, I'm honored to have the opportunity to address you today. I was asked to speak about the social sciences and climate research, and specifically about the benefits of integrating socioeconomic aspects into climate models. First, as a matter of clarification, the models that I address are those that project greenhouse gas emissions from human activities and simulate policies and actions to reduce these emissions. I would like to make the case today that we need more social science research to understand how different communities around the country may be impacted by and respond to climate policies. These energy climate models can support the design and implementation of climate policies by incorporating insights from such research into realistic projections of emissions reductions so that we can more accurately assess progress and the best path forward to achieve our targets. Our energy systems are embedded in social institutions. The changes implied by our targets are potentially far-reaching across society, involving not only how we produce and deliver energy, but also how we use energy. These changes may affect our homes, how we get around, as well as how we organize our lives. Achieving the scale of transformation in society requires turning knowledge into action, action by government, organizations, and individuals. And understanding the social processes by which these actions can lead to transformative change is the domain of social sciences. My focus today is specifically on households, how energy climate models represent household consumption behavior and their response to policies. The motivation for my focus is twofold. First, there is wide recognition that climate change is a matter of social justice and equity. We know that low-income communities globally are likely to face a disproportionate burden of climate change and of efforts to mitigate its effects. Racial and income inequalities in energy burdens in the US are already stark. Low-income Black communities spend more than double the share of their income on transport as the average American, while a third of them have no vehicle and poor transit options. Mortality during heat waves is higher in low-income communities, very likely due to lower use of air conditioning. The social sciences offer a rich understanding of poverty and structural inequality. We can draw from these insights and research approaches to better understand energy burdens on which we will impose new policies and technologies. My second motivation for focusing on households is that climate researchers have identified many changes in our lifestyles that would improve our well-being, such as health, and reduce emissions. For instance, walking or cycling to work, riding transit in cities, reducing waste, using products longer with more care, can reduce overall material use and free up societal resources to improve our lives in different ways. However, we need more research in the social sciences to examine the scope, feasibility of these changes and realize the potential benefits. Let me speak specifically of the models. Energy climate models have been instrumental in getting us to this point. They have helped us understand how human systems drive emissions growth, the portfolio of technologies we need to mitigate climate change, and the pace of decarbonization required to avoid the worst effects of climate change. These models are widely used by different communities, including policymakers, the finance community, development agencies, and researchers who want to understand what to expect from future climate policies. However, these models have simplistic representation of households. For instance, they typically model single representative households per region. As we move to implementing policies, it is critical that we disaggregate households based on structural differences, such as income, contextual factors, such as whether people live in cities or suburbs or rural areas, and assess non-economic considerations, such as health, all of which influence decisions. Household decisions in these models also neglect social norms, peer effects, and various constraints that shape decisions. For instance, homes located near those that have rooftop solar panels are more likely to invest in them themselves. Financial constraints, the digital divide, poor electric charging infrastructure may all be barriers to widespread adoption of new electric mobility options. And making these effects more explicit in models can enable more realistic assessment of technology adoption. Energy services are instrumental to meet other needs. Poor transit limits job opportunities, access to nutritious food, and the scope for other activities. Our energy use impacts others' well-being, such as through air pollution. New electric mobility options could reduce local air pollution, but they may increase pollution from power plants, which can affect other communities. So in conclusion, with more social science research, we can develop a more systematic understanding at a local level of the impacts of future policies on our climate goals, on equity, and on our overall well-being. And by integrating this research into climate models, we can link local policies and responses to national and global emissions targets. We can assess the broader social impacts of an energy transition and more realistically track progress in achieving our long-term climate goals. Thank you for listening. I look forward to your questions.
Thank you, Dr. Rao. At this point, we will begin our first round of questions. The chairman recognizes himself for 5 minutes. Dr. Rao, thank you for your fascinating testimony. I want to follow up on your comments about climate policy focused on well-being. I believe we need to break out of the simplistic economic assumptions that too often shape the parameters of policy, and your remarks underscored that for me. In a country where the rich have massively higher carbon footprints, achieving a fairer distribution of wealth is a matter of climate policy. Giving people more time to care for and enjoy their loved ones is a matter of climate policy too, because we need to shift away from harmful kinds of consumption and towards an abundance of the things that genuinely improve quality of life. If we went big on investing in the modeling improvements you described and integrated cutting-edge social science, can you say more about the different kinds of possibilities that might be opened up? Would that kind of modeling allow us to demonstrate how climate action and building a better society can go hand in hand?
Yes, sir. I do believe there are many opportunities that are opened up to seek a more equitable society from pursuing climate policies that we assess in models that assess a wide range of impacts besides economic impacts. So I'd like to classify them into two types of opportunities. One of them is to be able to alleviate some of the existing burdens that people already face from their energy situations. So for instance, if we think about people who live in inner cities who don't have access to transit today, they may not have vehicles, and the existing options may be too cumbersome for them to really travel outside their neighborhoods in order to seek employment opportunities or seek places where they can buy nutritious food. New mobility options, such as car sharing options or introducing new routes, electric buses, for example, these could potentially fill a gap in their existing services that they receive today. And so if we can understand with social science research these vulnerabilities that people have in different parts of the country, understanding the actual energy burdens they face, not only economic, but actual deprivations of energy services, we may find ways that these new options could actually meet some of these needs that aren't being met today. Another example might be heat stress. If we understand better the extent to which people are not using equipment today in order to keep their homes cool in summer or warm in winters, we can potentially think about upgrades to buildings that can offer new technologies that could alleviate problems such as respiratory illnesses due to mold. It could make sure that they have the ability to affordably heat their homes as well, or cool them in summer. So those are some of the options that we can exploit with these new technologies, and social science can help us understand the potential for that. There also are other range of opportunities that we open up in thinking about well-being when you consider a broader consumption. So for example, we may think about the fact that we waste a quarter of our food supply, and that has an impact on greenhouse gas emissions. We have a lot of congestion and air pollution from our use of private vehicles in cities. If we introduce policies that can encourage people to use transit, to share vehicles, we can reduce air pollution, which may affect particular communities, and we may raise the overall level of resources that are freed up by reducing waste and channel them to improving our well-being overall. So those are some of the examples.
Thank you, Dr. Rao. I want to try to squeeze in one more question. Dr. Takeuchi, thank you for your testimony as well. I want to zoom in on what you said about training the next generation of scientists and leaders and ask if you have further reflections on that subject. I may be biased, but as a former teacher and principal, I tend to think that education is the answer to everything, and particularly more equitable education, so that we are tapping into the potential of communities that have seen decades of disinvestment. We've had several discussions on this committee about the role of education in preparing our young people for the green energy transition. Given what you've told us about the importance of interdisciplinary research and collaboration across different aspects of a scientific problem, do you see ways that we can infuse those principles into STEM education more broadly, particularly at the K-12 level?
Thank you, Chairman. I'm going to have to speak quickly here. I think part of the key is to making sure that everyone is included. I'm extremely proud of our own research group that is highly diverse, not only in ethnic and cultural background, but gender as well. The FRC team that I assembled is also highly diverse, and I think demonstrating to people that everybody counts is a key aspect of showing people that there's an opportunity for them so they don't feel left behind or excluded.
Thank you. I now recognize Mr. Weber for 5 minutes. Oh, excuse me.
I'm here.
Disregard. Who's next in line to ask questions? My apologies.
Mr. Weber's next.
Thank you.
If I can figure out how this machine works, I can do this. Can y'all hear me? Mr. Chairman? Okay, thank you. Dr. Pearson, in your opening, like I mentioned, my opening statement, I recently introduced the CAMS Act, which I hope, and I think you will, I hope you will, agree really touches in a good way on a critical area of research. In addition to establishing computational materials and chemistry science centers and a materials research database, my bill aims to improve materials science research by applying advanced computing practices to emerging chemistry and materials science challenges. It did not escape me that one of the other witnesses, I think it was Dr. Takeuchi, said that we are in a race. And boy, she's right about that. Anyway, Dr. Pearson, you said in your testimony that 45 million data records are requested and delivered daily, and tens of thousands of community researchers log into the materials database every single day. If you could quantify it, how much or what percentage of that data is being fed into advanced computers or artificial intelligence algorithms, number one, first question. Number two, how unique do you think the DOE's computing resources and knowledge, how unique are DOE's computing resources and knowledge, and how would they help improve your particular materials research? And I'll stop for your answers.
Thank you for that question. I am passionate about this subject. This is the foundational work that the Materials Project relies on and hopes to bring to the future. Your question was first about how much of the percentage of the data that gets fed into AI and machine learning. The best answer I can give to that is that every day a paper is published using Materials Project data that uses also the word machine learning. It's hard for us to track exactly how people use data, but that is one way we can use natural language processing to look into papers rapidly, even though so many are published every day, and literally say, okay, they mentioned the Materials Project and they mentioned machine learning. Every day a paper is published doing that. We have seen a tremendous increase of the number of data points that the Materials Project delivers, is requested and delivers every day. From the last couple of years, with the acceleration of machine learning as being such a popular and powerful way to address materials innovation and design, being the only database that gives this many properties for materials available, this is why we're seeing such a tremendous increase. Your question, the second question, was on the DOE computers. They are amazing. We would never be able to do what we do today without them. I have had tremendous support from, for example, from NERSC at Berkeley Lab, but also from places like NREL and Argonne in terms of using their computers. There are different kinds of computers useful for different things. If you're doing climate modeling or social sciences modeling or materials research modeling. And the one thing I would say is that we need a diversity of computing architectures to address all of those different kinds of computing needs. And I'm really happy to see that those are being met at different kinds of computing centers in the US.
So would you say, is do you go on site to use those computers? How often do you interface with those computers?
We run 24/7. Thankfully, I don't have to go there in person. Our scripts and our algorithms run every day, 24/7, as long as they have uptime. Sometimes they go down for maintenance, but that's the only time we don't run.
And when you say a paper, there's many papers every day published.
Yeah.
You're right. This is absolutely fascinating. Who keeps up with those papers? How do you talk to your colleagues? Who decides what papers? What's the best article? I know you're limited by time.
No, that's a great question too. And we are struggling with that. There's no researcher today that can physically read every paper that's produced. So we're actually starting to use automated ways to analyze which papers to read and how to read them. So like I mentioned, natural language processing is a way for machines to read papers and to extract the knowledge from them. Actually, we have to, in my opinion, papers are wonderful. They're storytelling vehicles, but we also need to actually get the data out of them more quickly. That's one way of doing it. But if we were better at putting the data in places like databases, like the Materials Project, we wouldn't have to go back and actually extract them from papers. So in my opinion, we should do better.
Well, and hence the need for advanced supercomputing in a major way. And I had a lot more questions, but I'll yield back. Thank you, Mr. Chairman.
Ms. Johnson is next.
Thank you very much, Mr. Chairman. Oftentimes, when people think of climate science research, they think of NOAA, EPA, NSF, and understandably so, because they may forget about the vital work of DOE and what they do in this space, such as contributions to the National Climate Science Modeling efforts to the U.S. Global Change Research Program, and the international level through contributions of the Intergovernmental Panel on Climate Change. I'd like to ask Dr. Zane, can you discuss what makes, can you discuss what makes the Department of Energy uniquely qualified among the federal government science agencies to conduct climate science research? And then to what extent do these agencies currently collaborate on climate science research?
Thank you for the question. I'm familiar with different federal agencies. When I think of DOE, I can think of a few unique aspects. The first one is DOE's climate model is optimized for the fastest computers in the world. This is so-called exascale computing. It is a big deal because the hardware speed of the supercomputers you can measure and benchmark. But what's equally important is what the percentage of that capability is actually used. And that depends on the architecture and the software engineering of the climate model. And the DOE is moving very rapidly in that direction. The lessons learned and the best practices of the DOE can be followed and will be used by other agencies and worldwide. The second unique aspect is about the coupled human Earth system model. There are around 50 Earth system models, and there are around 10 human system models in the world. And only DOE is in the process to bring them together. So with time, I just give you those two examples. And then in terms of the multi-agency collaborations, there are already some interactions at different levels. Scientists supported by different agencies are talking with each other all the time. And the program managers from different agencies are talking with each other. Even today, we are having our scientific steering group meeting. So I escaped from that meeting, come here to testify. And there we have managers from different agencies in the US and also worldwide. And also there are cross-agency collaboration mechanism, such as the US Global Change Program. But I still more can be done, particularly on big projects. Give you an example. If you cannot balance your checkbook, you don't feel good. But if we ask, we cannot balance our water for major basins, for Mississippi, for Colorado, as scientists, we do not feel good either. In other words, we don't know exactly how much water go to the Colorado River Basin, how much water come out, and where are the sources and the sinks. And the community wants to have a big projects working together with different agencies to solve this kind of grand challenge. I will stop here. Thank you.
Thank you very much. One other question. In developing legislation to reauthorize the activities of the Biological and Environmental Research, the BEAR program within the Office of Science, we've heard from stakeholders that there's a gap in research funding mechanisms. I understand that this program funds large-scale experiments, and the user facilities we've heard a lot about in this hearing, and also small individual research grants. But there's no in between. So do you think that the BEAR program could benefit from having a mid-scale funding mechanism to fund research that would be carried out by multiple institutional research centers, similar to the Office of Science's Basic Energy Sciences programs and supports the Energy Frontier Research Centers?
Make it simple. It's a great idea. I just hope add one more point. Those university partners should also include the involvement of underrepresented groups, such as students from minority serving institutions and historically Black institutions and universities. Thank you.
Thank you very much. I yield back, Mr. Chairman.
Ranking Member Lucas is next.
Thank you, Mr. Chairman. And I would address my questions, my inquiries to all the witnesses. As I mentioned, SALSTA doubles our investment in basic research at the Department of Energy over the next decade. What role do you think DOE's Office of Science and its national laboratories play, or perhaps I should say, should play, in enhancing our competitiveness with other nations in science and technology? And while you're thinking about that, what if anything, should we be doing to enhance DOE's role in our federal research enterprise as we seek an edge over international competition? And I throw that open to the entire panel.
Let me just make a few opening comments. I think BES investment is really critical because it does lay all of the foundational science. And I think that the continued DOE investments in the more applied offices are also critical because we need that translational infrastructure to ultimately end up in the private sector as well. So the way I see it, that there's really four circles: academics, national labs, industry, and let me add policy, all need to work together to advance the field to accomplish what you're talking about and having international competitiveness.
Anyone else care to touch on that?
Yes. From the BR side, there is substantial competition from our partners in Europe. They are very aggressive in terms of supporting big science. And our hope is on the BR side, we want to maintain our leadership in terms of the CARBOT's human Earth system modeling, the integration of modeling with exascale computing, and our observing user facilities in each area. Again, even today, we are having the international steering committee meeting. You can see they are very ambitious projects supported by EU. And on the American side, the DOE is always about the big projects. Besides the small, and now we talk about the mid-size, we need those flagship big science projects to maintain our leadership.
Anyone else care to touch on that subject matter, the question?
I'd be happy to. I completely agree with the latest comments. I have collaborators and colleagues in Europe and also in Asia. And what I can see, for example, the materials projects funding, they are getting funding that are 4 times that. They're still behind us because, quite honestly, American innovativeness is hard to beat. And we're also the first ones to do what we did. But in the end, funding will matter. So that is the one big vehicle. I see the tremendous passion that the scientists at the Molecular Foundry and the NSRCs and the labs have for working with our community, doing that better, bringing in vehicles that allows, for example, professors and graduate students and postdocs to travel from the rest of the country to be part of the knowledge sharing and the ideas that we leverage to solve our future problems. That would be a big deal for the user facilities and for our communities in general.
Anyone else?
Sure. I just add one
Please.
small point here. Wanted to mention that the European Research Council have recently seen their strategic plan over the next 5 years for research, and they've allocated $15 billion towards climate. And one of the main elements of their strategic plan is to have social science and humanities research be a core part of every single cluster that they have announced. And so I think, interdisciplinary collaborations between the sciences and social science to really understand how we can have widespread adoption of these technologies, I think would be also valuable.
In my few remaining seconds, and I have to ask from both perspectives, what, if anything, we should not be doing? We should not be doing. And you don't have to answer, but your insights are appreciated.
Yeah, I do have one comment here. I don't have a direct answer, but I feel accountability and the metrics for success is crucial.
Fair enough, Doc. With that, I see the balance of my time is expiring. Thank you, Mr. Chairman, and I thank all the witnesses for their insights today.
Ms. Bonamici is next.
Thank you so much. Thank you, Chair Bowman, Ranking Member Weber. Thank you especially to our witnesses for your expertise. This is an excellent discussion this morning. I represent Northwest Oregon, and here the climate crisis is not a distant threat. It's really a reality. We see it in many ways. And the need for robust climate science will only grow as our communities and our economy experience the increasing effects of the climate crisis. I'm honored to serve on the Select Committee on the Climate Crisis. Last year, we released our bold, comprehensive, science-based climate action plan to reach net zero emissions no later than mid-century and net negative thereafter. And we acknowledge that we need high-quality, peer-reviewed climate science to serve as the foundation for our efforts to solve this crisis. Our plan calls for robust climate science research, observations, monitoring, and modeling activities, including support for Earth observations, climate model development, international collaboration, and improvements in data and computing infrastructure. And I know certainly on this Science, Space, and Technology Committee, we have a lot of support for quantum computing, and we've shown that over the years. Dr. Zhang, I'm the co-chair of the Bipartisan House Oceans Caucus, so I'm particularly interested in your research on the land, atmosphere, ocean interface processes in the Earth system. How can efforts through the Biological and Environmental Research Program within the Office of Science better inform our understanding of sea level rise and other effects of the climate crisis on coastal communities? And following that, Dr. Rao, how can we make sure that this research better integrates socioeconomic modeling to support frontline communities in those coastal regions? Dr. Zhang?
Yes. You pick up all those red topics. Actually, DOE's climate modeling at this time has 3 focus areas. One of them is sea level rise. In terms of the Antarctic and Greenland ice sheets melt, how does that affect sea level rise? And then for Oregon, of course, is a coastal state. And the DOE just initiated a new program on the coastal study for the interaction between ocean, land, and atmosphere. So obviously, DOE research and the results will directly benefit states like Oregon. Even for my own research, it's directly relevant to say our nation's weather forecasting. My group has contributed the software development for the weather forecasting every single day over ocean and over land, of course, including Oregon. Now, in terms of the social science side, DOE does have a multi-sector dynamics program that's about the human system modeling. There, human activities are included, things like urbanization, irrigation, agriculture, deforestation, for example. And the socioeconomic projections are also included. What has not been treated well is about the human behavior. We are human beings. We have a lot of local decision-making process. Those are the processes.
And I don't want me to cut you off, but I want to ask Dr. Rao that question as well. And then I have one more question I want to try to get in. Dr. Rao, can you add anything to the social services, social sciences aspect of the ocean and economic modeling?
Yes, thank you very much. Just to build on what Dr. Seng was saying, which I agree with, we need a deeper representation of households, which includes looking at their spatial granularity. So understanding what populations are located on the coast, what are their characteristics in terms of income and other attributes. We need to understand the physical infrastructure around them in order to assess the vulnerability to sea level rise and other impacts. We need to think about migration into coastal areas and away from coastal areas, and under what conditions people are amenable to that. And there are models that are trying to look at that in terms of climate resilience and adaptation, but we need a lot more granularity to really understand and make them responsive to future conditions.
I'm going to get one more question in. Dr. Takeuchi, in your testimony, you talk about the importance of teamwork, working in partnership to develop new generations of battery and energy storage. As a longtime advocate for integrating the arts into STEM education, I truly appreciate your arts analogy of a symphony orchestra bringing together, with a conductor bringing together everyone. You talk about that in your collaboration potential of the Energy Frontier Research Center. So recognizing that the existing lithium-ion batteries will not meet the growing need for more complex energy storage challenges like electric vehicles or clean energy grid. How can the Basic Energy Sciences program better support that type of collaboration to accelerate the development of clean energy technologies and energy storage?
I do think that the programs such as the Energy Frontier Research Center and the hubs are really outstanding vehicles to bring together teams of scientists and technologists and engineers to focus on kind of mission-driven science questions. So I think that those vehicles should be maintained, expanded where possible, because they're outstanding concepts that allow addressing exactly the point that you're making.
Thank you so much. I yield back, Mr. Chairman. I wish we had 5 hours per member instead of 5 minutes. Thank you. I yield back.
Mr. Baird is next.
Thank you, Mr. Chairman and Ranking Member Weber. I appreciate this opportunity, and I really appreciate the insight from the witnesses that we have here today. You know, as Ranking Member Lucas mentioned, I introduced the Department of Energy's Biological Innovation Opportunities, the BIO Act, today, and it is to support DOE's Biological Research Infrastructure Initiative, which would include reauthorization of DOE's bioenergy research centers and establish a program for the construction of biological and environmental research user facilities. And, you know, one example we've talked about across various disciplines in our discussion here this morning. And, you know, there are multiple benefits for society that are derived from the Department of Energy's Office of Science Basic Research. And we are constantly looking for sustainable domestic biofuels and bioproducts that are derived from non-food lignocellulose plant biomass. And for those of you that might be interested, lignocellulose is the most abundant biological material on Earth, and it's most often contained in plant cell walls. It's made up of long, tightly bound chains of sugars, polysaccharides, that can be converted to biofuels and bioproducts by microbes. And so I'm making the connection here because of agriculture and the role they might play, or it might play, in this energy solution. But my question really deals with knowing the importance of this interdisciplinary Office of Science Research and how important that can be. My question to the witnesses is how your perspective, what opportunities there are for additional BER user facilities. So I really want to focus on those user facilities, what we might derive from expanding and increasing the number of those. So Dr. Zhang, would you care to express an opinion on that?
Regarding biofuel or crops, the good news is the DOE climate model actually includes the treatment of biofuel crops in the model. So that means we can look at the potential impact in the modeling system. For the biofuel itself, that's not really my research area. Probably I should not say anything I don't understand.
How about any of the other witnesses? You care to address that question about biofuels and the importance of research and the interdisciplinary connectivity?
Representative Baird, I wanted to comment on your question regarding research facilities and infrastructure. And I wanted to point out that, for example, the synchrotrons are used very often in biological and pharmaceutical and clinical type investigations. So I think that the fundamental infrastructure in terms of both the nano centers and the large scale synchrotron facilities are also highly relevant to the questions that you're asking regarding biofuels and understanding the fundamental physiology and mechanism of plants.
Anyone else? Go ahead.
I'll just add that even though this is not my core expertise either, the beauty of the NSRCs is that we have many different floors of many different expertise. And one of our floors in the Molecular Foundry is the biofloor. And they work very closely in partnership with the JGI, the Joint Genome Institute, that actually works on biofuels. So the number of user facilities that work together, from the characterization of the light sources to the nanocenters to the BER user facilities, they're all actually, that's part of the teamwork too that we've discussed previously. And I would like to highlight that it's a vital part of that innovation.
Very good. Anyone else have a comment? If not, I yield back the balance of my time. Thank you, Mr. Chairman. I yield back.
Mr. McNerney is next.
Well, I thank the chairman and I thank the witnesses. This is a great subject. I majored in chemical engineering and then switched to mathematics at some point in my career, but I really appreciate the testimony. Dr. Zhang, cloud aerosol research and computing seem to help us understand some of the key climate challenges, but uncertainty in how aerosols impact on clouds seem to hinder our ability to determine climate sensitivity to greenhouse gas levels. Reducing this uncertainty will improve our ability to forecast weather and climate. How critical is increasing investment in the modernization and acceleration of the Energy Exascale and Earth Systems Model Program? Dr. Zhang?
Yes, I'm thinking of two things. One is the research and one is the application. On the research side, for example, a couple of weeks ago, news media asked me about hurricane activities because there are above average hurricane activities 5 years in a row. This year, we predict another above average hurricane activity. How can we predict hurricane activities in the future? If we use today's climate model, the grid size is 50 miles. You cannot even see the ice. What we need would be at least 5 miles grid spacing, and the DOE computer and the climate model can do that to help the fundamental understanding. And then for the application sides, I'm thinking about the DOE climate model can be used for the planning to assist in the planning of our nation's energy and related infrastructure through scenario analysis and trade-off analysis, and by working with the applied programs of the DOE.
Well, you mentioned a 2 mile resolution, so we have a little ways to go on that. Then a 2 mile resolution is what you prefer. How essential is artificial intelligence to climate models?
It's crucial because the data volume becomes huge. Frankly, we human beings don't even know how to handle them anymore. So we need artificial intelligence from different perspectives. First, help us to save computer time. Second, help reformulate the model processes. And third, help us to do the uncertainty quantification and whenever possible, the uncertainty reduction.
Thank you. Dr. Brushett, in November of 2020, the Wall Street Journal published an article in which Dr. George Crabtree, director of the Office of Science's Joint Center for Energy Storage Research, discussed the crucial role that AI plays in the battery materials discovery process. What roles do emerging technologies such as AI and robotics play in battery storage and AI development and battery storage technology development?
Thank you for this question. And I think also Dr. Pearson can also answer to this, but I'll give you a first pass. I think AI and machine learning dramatically accelerate critical activities like materials discovery and materials synthesis, which are two vexing bottlenecks in the development of new technologies. They do so by finding sort of hidden correlations between desired performance metrics, which we could calculate, and actually then finding the structure and composition of materials that would be able to meet those desired performance metrics. These correlations can then define new classes of materials that will likely exhibit those desired properties and performance. It's tens to hundreds of times faster than searching for new materials by laboratory or by sort of brute force computation. Long used in drug discovery. I think that this is the next wave for discovery for energy storage materials and material science in general.
Thank you. And I was going to follow up with Dr. Pearson on the same question. I am interested in AI. I'm co-chairman of the AI caucus in Congress, and the use of AI in battery development and the researchers' ability to interact with the AI-driven insights. Could you discuss that a little, please?
Absolutely. Thank you so much for your support of science and Berkeley Lab in particular. So material science is not like the social sciences or like they can leverage Google. We're actually data poor in many cases, which is so important to also have a vehicle for harnessing our data wherever it comes from experiments, from computations, so that you can actually train machine learning algorithm on top of that data. So the first part, and I always liken this to like your machine learning algorithm is a Ferrari, but you need fuel, the data, to actually run it. The automation, and I know I'm over time, is a really critical aspect to it too. If we have more time later on, I'll be happy to elaborate on that's needed to close the loop between the modeling, the synthesis, and the characterization faster.
Thank you. And I'll be visiting the Molecular Foundry sometime as soon as I can.
Fantastic.
Mr. Feenstra's next.
Thank you, Chairman Bowman and Ranking Member Weber. Thank you to each of the witnesses for their testimony and sharing their extensive research and opinions with us. The research and collaboration lead by the Department of Energy's Office of Science is crucial for the future of American energy. I represent Iowa's 4th District, a leader in wind energy. So I am thankful for the ongoing research into new energy storage technology and critical materials that are important for renewable energy. And with our state being a leader in clean burning biofuels and other forms of bioenergy, I appreciate the work being done at the Office of Science and Biological and Environmental Research Programs. I have a question for Dr. Taguchi. I was pleased to read about your research about leadership at one of the Energy Frontier Research Centers. It truly is a unique model that you pointed out that is similar to a conductor who understands an orchestra music results from just one person and all the orchestra pieces playing together. Your specific EFRC focuses on scalable electrochemical energy storage systems, which are crucial as we grow wind energy in my district and across the country. Elsewhere in the Office of Science and Biological and Environmental Research Programs are the bioenergy research centers. And in my district, Iowa State University is a partner in one of these BRCs called the Centers for Advanced Bioenergy and Bioproducts Innovations, which focuses on increasing the value of energy in crops and converting biomass into valuable chemicals. So this is my question. My question to you is, at what level of interaction do EFRCs have with any of the bioenergy research centers? And what role do bioenergy research centers play in being part of this group of people aiming for this common goal? Is increasing collaboration something that I could, or we in general could assist on moving forward? Could you comment on that?
Thank you very much for your question. I just have to say really quickly, I understand your interest in wind energy. I live on Long Island, and soon we will have some of the greatest offshore wind energy in the entire country. So we will face similar challenges for integration. One of the things that DOE does very effectively is bring together the different energy frontier research centers in things called principal investigator meetings, where the different centers focused on different areas come together and share their research and findings to facilitate interaction among the different groups. And I think that could be readily expanded to not only include BES, but BER as well, where cross-population and cross-fertilization of ideas and findings could really be facilitated. And by sharing the findings, the different groups can then internalize how those findings would be relevant to their specific areas of research, even though the specific thing that they're researching is different. And that can be a really effective way to kind of fertilize that interaction and make sure those communications take place.
Thank you, Doctor, for that answer and those comments. I have one other question for everyone. One of the newer technologies that I've heard promise about is in regard to fuel cells. As you know, fuel cells can use a variety of fuels, including bio-based fuels, which is of particular interest in Iowa. In fact, Dr. Pearson of Lawrence Berkeley National Laboratory has been awarded funding to conduct research into metal-supported solid oxide fuel cells for vehicles that can be used as part of the rapid start fuel cell system that uses the liquid bioethanol as a fuel. This is just one example of how biofuels could fit into future fuel technologies that dramatically lower our transportation sector carbon footprint. An open question to all witnesses: do you think we should drive more research into renewable fuel technology as an alternative to petroleum?
Maybe I'll start. I think that it's one of the beauties of biofuel is that we already have an infrastructure for liquids. And it nicely also ties into our climate mitigation. If we could harness CO2 and turn that into viable products, which is something that we work on from LISA, which is the continuation of JCAP, one of the innovation hubs, of how actually to turn CO2. And that is also a materials problem, right? You have to actually come up with a catalyst that helps you to turn CO2, which is an extremely stable molecule, into a liquid fuel that you can burn and become carbon neutral. At the Foundry, we also have several users that come to the Foundry with exactly that dream. They come from places like Houston in Texas or out in California, and having seen their environment, where they grew up, and the climate impact on that environment, and they bring that passion and they bring their ideas to places like the NSRCs, and we work together with them to find solutions. We have startup companies that work on CO2 capture and turning that into actually a viable fuel. So that is it's similar problem, but I'm going to turn it over to others to let me have.
No, thank you so much, and I yield back. I ran out of time, but thank you so much.
Mr. Caston is next.
Thank you so much. This panel is I don't mean to get all scientific, but you guys are awesome. I'm learning so much here. I really appreciate it. I got concerned several years ago that as we are deploying increasing volumes of intermittent renewables on our grid, we have the potential to start seeing increased CO2 emissions, not because the renewables are generating CO2, but because the only tool grid managers have is really inefficient, partially loaded but quickly ramping gas cycles that ramp up and down to balance. And we started seeing some evidence of that in the Midwest where I'm from in Illinois a couple of years ago. And that was really what drove me to introduce the Grid Energy Storage Act last term, which worked with Congressman Foster, became the BEST Act, which was signed into law by the prior administration to put about $1 billion into research, development, and deployment of grid energy storage, because of course we're either going to do grid energy storage or transmission to solve that problem. There are not a lot of other solutions to it. Hopefully we will get that appropriated shortly, and it will help support some of the research that all you people are doing here. But I want to start with you, Dr. Takeuchi, given your expertise on grid energy storage systems. Can you give us some sense of where are we at best in class right now, especially around energy density and cost per kilowatt hour, and where do we need to get to before we're really going to have commercially viable grid energy storage systems to start to balance out some of those imbalances in our system?
Thank you very much for the question. In terms of energy density, my own personal belief is that for installed systems, the energy density itself is a little bit less critical than in applications like vehicles or portable power, because most of the time it doesn't have to move. We put it in place and it sits there. I think that the two critical things really are longevity and cost, and they're related. Longevity is extremely important because then you can amortize the cost over longer time. If the thing can last longer, you don't have to replace it as often. So I think we're still a distance away in terms of the cost targets that the utilities would like to see. I interact with many utilities in the Northeast to understand their needs and concerns. And I think another area that's really critical is the understanding and the education and the interaction with the ultimate customer, meaning the utility and then the ultimate user, to make sure that the energy storage technologies that are deployed in an effective way, such that their longevity, their lifetime, and their efficiency is maximized through the use profiles. So we're developing modeling systems on that integration question to make sure that when the energy storage is integrated, that it's integrated in the best place, best location, and with best usage profile to, let's say, optimize the cost deployment profile. But the amount of research dollars that has been invested in grid scale storage is still far, far, far less than things like vehicle technology, et cetera. So there is still work, definitely, that needs to be done.
Well, thank you. And I could ask Dr. Bruchett or Dr. Pearson the next question, but I'm going to go with Bruchett only because I started my career at Arthur D. Little over in Fresh Pond, and we cross-pollinated with a lot of your folks over at MIT. And of course, now Argonne National Lab is just south of my district. The Advanced Photon Source, which of course is part of the BES program, has done all sorts of just fascinating things to develop some of these advanced battery chemistries. In the minute or so we have left, can you maybe just share with us some of the tools that we can use through that APS program to help develop these larger scale, particularly in the grid energy storage batteries?
Thank you. I'll do my best in the time that remains. And if you would like some more information, we can certainly follow up. So I think one of the things that Professor Takeuchi mentioned was lifetime associated with grid scale batteries and understanding how those batteries might decay over the lifetime and establishing mitigation strategies early on to allow them to last for longer and to allow us to use cheaper materials. A lot of the phenomena that we need to see are atomistic changes in catalysts or in electrode type materials within that battery. And being able to see those often requires resources that you need to penetrate into an operating battery and see how the dynamic processes are occurring on that interface. It's not possible to do that at top tier research facilities like MIT. You really need synchrotron resources and those powerful X-rays to peer inside the battery and understand where decay mechanisms are coming from. And so that's how we've been using it to understand how we can extend lifetime of these new materials.
Thank you so much. I'm out of time and yield back. Dr. Pearson, I'm sorry I didn't get to you, but if you do have more comments, please feel free to follow up with our office. Thank you.
Mr. Jimenez is next.
Thank you, Mr. Chairman, and it's been really fascinating listening to all the experts and the questions. I share my colleagues' fascination with fuel cells, and think that is a viable alternative to large-scale batteries on transportation, simply because of the refueling time and the impact that actually, if we moved everything into electric vehicles, the impact that's going to have on the grid. And also, how do we dispose of these batteries at the end of their useful life? I don't think we have a great answer for that. So, but regardless of that, my first question, I guess, is Dr. Pearson, and where do you think the United States lies right now in terms of computing power? Are we number one? Are we number two? And is the world catching up with us?
That's a good question. I think the way I would see it, there's competitiveness out there. I'm not entirely sure we're number one, but the number one question is a multifaceted question. Is it really just the exascale? Like how fast? Is it really just how many CPU hours you're getting? It's or how many of those processors you have. The important part is that we invest in the computing that will drive our innovation forward. So I'll give you an example. Some of our computing centers are particularly well suited for certain algorithms. Some algorithms that I run can only run on other computing systems. So it's important to ask the question, maybe, what computing do we need to solve today's and maybe the next decade's problems? So for example, machine learning algorithms run on certain computers. The kind of algorithms that material scientists run on other kinds of computers. And I do think in terms of those, we're world leading.
How fast is the world catching up to us? And who is our leading competitor? I already know the answer, so go ahead and answer.
I would venture to guess that China is our competitor when it comes to the computing.
Okay. In terms of artificial intelligence, because I think that's the great leap that we have to win the race to artificial intelligence. Once we do that, then I think that the knowledge that we have and the ability to take unlike concepts and put them together and come up with something revolutionary is just going to take off. And so, where are we in terms of the development of true artificial intelligence? And again, how close is our nearest competitor, or are we lagging behind right now in achieving that?
So there are two aspects to artificial intelligence. It's the data part and it's the machine learning part, the algorithm part. The machine learning algorithm part is very tightly integrated with our ability to compute fast and efficiently in certain ways. So for example, quantum computing is one of those avenues towards actually making artificial intelligence a reality. If I were to bring that back to my field, because I would have to refer to experts in computing architectures to really truly talk about that aspect. If I bring it back to my field, quantum computing is inherently tied to materials. We don't have the materials today that can realize quantum computing in a cost-efficient way, that operate with higher coherence. They can actually have those electrons talk to each other without losing signal across information flow. That is a materials problem, and that's one of the problems that we work on as material scientists, to try to enable the materials that can do that kind of talking lightning fast, literally.
Is that a material?
Yes.
Is that a material problem just for the United States, or is it a material problem that the world has?
Everywhere. That is a fundamental global, and I would say pre-competitive problem in the sense that the mechanisms for decoherence, for losing that signal strength, is a pre-competitive problem that BES funding is coming into. The actual material that eventually will go into a quantum computer, a truly successful one, that is more of the sort of more proprietary pathway.
What can we do as a government in order to help you? I know it's going to be money, but what else can we do to help you to achieve for the United States to be the leader in artificial intelligence and computing and maintain its leadership?
So I would say that, again, going back to those two pillars, right? The computing, the materials aspect, and the data. We need data to actually train machine learning algorithms. They don't work. They cannot operate without huge amounts of data to train them. We are not leveraging the data that's already being produced today in our user facilities, in our basic research programs, because it's such a huge amounts, right? And that's great. That's awesome. That means our scientists are immensely productive. But imagine now that you harnessed all of that data and you learned from it more than just reading an article, which is hard enough to keep up with. If we harnessed our data in a more efficient way today, we can not only train machine learning algorithms, we've been much more efficient in using the knowledge we're already sitting on.
Thank you so much. And I guess I'm out of time. I yield back. Thank you.
Mr. Lamb is next.
Thank you all for hanging in there with us and for appearing today and sharing all the information that you have. I wanted to ask, I think maybe this is a question for Mr. Brushett, but I'll leave it open to anybody. With respect to the state of things today for grid scale battery storage, is it correct to say that in the United States, the length of time that any grid scale battery installation lasts is somewhere around 4 to 6 hours at most? Is that like an upper limit of where we are today?
In terms of how you might want to use that application, yes, most of the applications would require 4 to 6 hours of storage or less. Is that what you intended to say, Mr. Lamb?
I think what I mean is just in practical terms, if we lose power generation at 10 o'clock at night, is there anywhere that lasts beyond 4 a.m. the next morning? My understanding was that was roughly the limit we are now in terms of intermittency and the ability to cover that period.
Yes, I understand. Yeah, and that is a correct understanding. Most of the backup battery installations that exist in the U.S. are designed for 4 to 6 hours, largely for at time of energy management, so shifting energy from one part of the day to the other.
Okay, and do either you or Ms. Takeuchi or anybody, do you guys have a sense of the time it will take us from today to transcend that in a meaningful way? You know, to get to not just 10 hours, but to 100 hours with specifically batteries. I know there's other storage technologies and everything, but just kind of the outlook for battery R&D.
So that's happening right now. There is ongoing research in long duration energy storage that extends to, we'll say, a day long worth of storage all the way out to a couple of days to say cover an outage that lasts for a week or a few days. Some of that work is sponsored within JCESR. One example is Form Energy, which is focused on, as you mentioned, a 100-hour battery. But some of that research nucleated in JCESR, looking at long duration energy storage with ultra cheap materials, and then ultimately spun off as a startup that became Form Energy. There's also increasing research within JCESR and other parts of the DOE as well on redox flow batteries. I mentioned a little bit earlier in my oral testimony. And these systems are designed for that 6 hours plus, right? The reason you want to go to a system like that is because as it scales out in terms of time, the cost of the installation reduces per unit energy based upon the system architecture. And so people are also looking into that as well. As was mentioned, I think a little bit earlier, the amount of investment as compared to the investment in energy storage for transportation applications is decidedly less. And that's an area that I think is going to become increasingly important as more and more locally available renewable resources come onto the grid and we wish to utilize those, we're going to have to think about ways to store that energy and deliver it in a dispatchable way.
Yeah, that's an important point, and thank you for emphasizing it. I know this is always a hard question to answer, but from what you know of the state of the research now, is it at all possible to forecast whether you think there would be a demonstration project of longer duration storage within the next 5 years, 10 years, 15 years? Do you have any idea what kind of time scale we're talking about there?
I personally am pretty optimistic. I'm not going to point to a specific example, but I think within the next 5 to 10 years, I'll put it this way, I think not only will it happen, I think it has to happen. So I think that's where the let me just echo what Vic said, that the investment in long duration or large scale energy storage, I think has been too low to be blunt, and I think that there's huge opportunity that and a lot of insight that can be tapped to get us where we need to be.
Great. Thank you all. I'm out of time. Mr. Chairman, I yield back.
Ms. Ross is next.
Thank you, Mr. Chairman. This has been a wonderful subcommittee meeting, and I really thank all of the folks who have come to testify. My question initially is for Dr. Rao, but if other people want to pipe in after he's answered it, please feel free. So I'm from North Carolina, from the Research Triangle area, and I've done some work with renewable energy and with integrated resource plans. And North Carolina was the first state in the Southeast to adopt a renewable energy portfolio standard. And in addition to adopting that standard, it created incentives for the regulated utilities to encourage conservation. Because as we know, if we conserve energy, then we don't have to produce as much, right? And so because you are working in multidisciplinary areas and trying to reach communities that might not be like the techie community I live in that looks at their smart meter and tries to figure out how to peak shave and do all of this, how can we use research, and in particular behavioral research, to encourage conservation, and what else should be added to enable communities that don't traditionally think about conservation to see it both as cost saving and a way to improve our planet?
Thank you so much for that question. That's a really important dimension. One aspect of this is involving customers more directly in reducing load, and that involves potentially using new technologies, smart appliances, smart devices, potentially having to be much more involved in your energy conditions, or thinking about energy costs. If you have a smart meter that tells you more information about your real-time prices and how you respond to them, we need to understand if people are able and willing to engage that much more in the effort to try and save energy. So I think we can do a lot of research on the customer side to understand behaviorally what will incent customers to really engage. And we need more research. That's qualitative fieldwork to talk to people, engage stakeholders. That's one aspect. I think we also need institutional research and understanding how we provide the incentives to utilities and to other agencies and to state governments to provide the kind of support that we need, both to prepare the grid in order to deliver that information to people, to understand the physical conditions of buildings, to know where we can maximize or get the most bang for the buck in terms of building shell improvements, for example, and also making sure that you have the right set of incentives for coordination amongst different players to make sure that all of these end up leading to significant long-term investments in efficiency. Because as you very rightly said, the more we invest in conservation, the less we have to invest to a greater extent in supply of energy.
And just one part of my question was, for less educated and low income communities who traditionally do not live places where it's easy to conserve energy and don't come from a culture where that's something that's valued, or it's complicated to figure. My mother couldn't figure out how to use an AMI meter. So what can we do to bridge that gap? Because not only will that help our environment, but it'll lower their energy costs.
Yes, I absolutely agree. There is a digital divide in some sense. There's an information gap. We know some things about it. What can we do about it? We can ask people. I think we need strong stakeholder engagement to understand what it will take for people to engage. And that's really what I think is the first step. I'd also mention we have a lot of publicly created data from national surveys that starts to hint a little bit at some of these conditions, people's education level, people's engagement with other technologies that we can use as a starting point. But we definitely need to ask people. That's my main message.
I only have a couple seconds left, so if anybody else wants to pipe in, please do so. Otherwise, I'll yield back.
I just wanted to comment that, at Brookhaven, we've created a department that I chair that brings together energy efficiency, integration, and grid modeling, as well as energy storage, because as you so correctly said, all of those questions are interrelated. Thank you.
Ms. Stevens is next.
Thank you, Mr. Chair Bowman. Dr. Bowman, this is just a real honor to be with my chair of the Energy Subcommittee on House Science and all of our fantastic witnesses. And also my colleague, the previous questioner, also from the freshman class of the 117th Congress, along with Chair Bowman, Congresswoman Deb Ross. This is just one of the examples of how fantastic the Science Committee is and the type of members that come onto it and help lead the charge. And of course, we're doing this work alongside the researchers and the experts and the doctorates, all of you who provided testimony today. I think Mr. Caston reflected on just the level of detail and expertise that you all have brought to today's hearing, which again is a part of Chair Bowman's effort to reauthorize some of the basic research funding in the Department of Energy, part of the reauthorization that we're doing with DOE. And one of the things I wanted to ask about with Dr. Zhang, and again, I'm holding your testimony and clutching it because I loved it. I loved all your testimonies, but I'm really can't take notes fast enough and all this great stuff that you covered. But I wanted to ask a higher level question just to level set what we're up to here today, which is about the role of climate science research and the role of the Department of Energy. And if you could articulate how that operates, what that looks like here. We're doing climate research. This is a major topic. There's a lot to delve into. We've got, obviously, you've got a NOAA, which is in the Department of Commerce. I guess some people are wondering about why, but NOAA's in the Department of Commerce, and they do a lot of this atmospheric work. But how are you using the Department of Energy and their basic research for climate science?
Yeah, I'll give you two examples. First one, earlier we discussed about the supercomputers. Okay, the speed of supercomputers for that beauty contest, you can say who is number one, number two, but that's not the most important factor. What's most important is what's the actual capability used by the end user, for this case, by the climate models. What DOE has done a great job is to recognize not only you need the hardware, you also need the scientific computing office and work with domain scientists, for this case, climate modelers, to bring them together to get the best computing capability out of the hardware. That's what DOE does very well. That's something will help other agencies and help the science overall worldwide. That's one thing. The second is about extreme events under climate change. DOE does not work on tomorrow's extreme weather, say, over any parts of the nation. That's a job for NOAA. But DOE's focus is about extreme events for the future with climate change. How do we prepare our national energy infrastructure for the future extreme events? What I want to see is modular interactions between the climate research and the applied energy research within DOE so that they can talk more with each other and use those knowledge for the actual planning of our nation's energy infrastructure for the future.
Thank you. Well, I know we've also touched on the grid. Obviously, the supercomputer consideration is major because of the cost, and you know it's expensive to access these supercomputers. And I know the chair has been touching on this too, which is the human capital considerations and the research opportunities. But do you feel, Dr. Zhang, that we are able to cover enough of the research with either the flow of applications coming in or the dollars coming in? And is there any confusion by writ of what the DOE does as compared to other agencies that are also covering basic research? Do we have to deal with any confusion? And as usual, 10 seconds left, so maybe I can take that to a written one, but if you have anything before we have to close.
You know, there is no confusion, but the competition for DOE research dollars is too fierce. To the degree, sometimes it's discouraging to the university investigators.
Great. Well, thank you all. Thank you for the whole panel. And again, to my chair, Dr. Bowman, I yield back.
Thank you so much. Before we bring the hearing to a close, I want to thank our witnesses for testifying before the committee today. The record will remain open for 2 weeks for additional statements from the members and for any additional questions the committee may ask of the witnesses. The witnesses are excused and the hearing is now adjourned. Thank you all so much. Have a great day.